Out-of-distribution samples refer to the test samples not well covered by the training data, like these black cats. They are misclassified with high confidence due to their black bodies. To explain why these samples are out of distribution, we developed OOD Analyzer, a visual analytics tool which provides an ensemble detection method and a grid-based visualization to detect and analyze out-of-distribution samples.
We propose an interactive ensemble analysis framework that provides flexible interactive exploration of the ensemble data. Time series characteristics of data can be obtained by fast browsing time steps. The region stability heat map view shows the stability of the selected region and provides region adjustment by directly clicking.
VisIS is a visual support system for the development of visualization algorithms. It has live compilation, automatic version control, predefined interactions, and tools for visual parameter analysis. By displaying the complete history of the algorithm, users get insights into the correlation between source code changes and visual differences.
How do you visualize the nanoscale, 1/1000th of a meter, for the public? As part of a Science Center exhibition, we developed an immersive environment that explains nanoconcepts by allowing users to explore nanoproperties. We reflect on how exploration, the confluence of explanatory and exploratory visualization, can be applied to visualization in public spaces.
We demonstrate that people can use the spatial cues available in virtual reality to help them effectively remember and recall scholarly articles. We used a virtual coffee shop and asked participants to remember 4 abstracts from scientific publications, and we termed this method a virtual reality memory palace variant.
Scatter plots and parallel coordinates are widely used for visualizing multivariate discrete data. However, for multivariate continuous data, the continuous scatter plots and continuous parallel coordinates are more suitable. In this work, we extend them to uncertain data. Additionally, we also extend fibers to uncertain data. If you are interested, come to our presentation.
This is a picture of a Tableau visualization within the browser. The data behind the visualization does not exist here, and Tableau is not running. This is just an image. However, parts of this image are fully interactive. Please join our presentation to see how we can share interactive visualizations across the web, free from any dependency on data or visualization application.
Asteroids have always been and will always be a threat to life on Earth. Most likely, an asteroid will hit deep water, but what properties will actually lead to a threat like a tsunami? Ensemble simulations are a common tool to understand the effect of different parameters like the size of the asteroid. We propose an interactive visual approach to help analyzing deepwater asteroid impact simulation ensembles.
Digital humanities present great opportunities for testing new visualization approaches and evaluation techniques. However, and given the diffuse character and novelty of the field, it may also be intimidating for novel and senior researchers willing to get started in the discipline. In this paper, we propose a data-driven analysis of visualization for the digital humanities to identify key themes, authors, and relevant publications. So if you want to know more, please read our paper.
How many clusters can you see in these images? With different visual encodings in scatter plots, our perception of cluster count changes. We developed models that consider how visual density influences cluster perception. Further, we demonstrate using a threshold plot to optimize the saliency of clusters.
White space surfaces are a novel approach to convey depth in vessel visualizations. The core idea is to shift all additional depth cues away from geometry and to use the usually empty space between the vascular structures. This allows us to display functional parameters on the surface and supporting cues on the background. We will explain how to generate such surfaces and how to use them as a canvas to further enhance depth and shape perception.
We present NL4DV, a toolkit that helps prototype natural language interfaces for data visualizations. NL4DV provides a high-level Python API for interpreting natural language queries. The API automates the core tasks of processing natural language queries to infer relevant information and determine appropriate visualizations, allowing visualization developers to focus more on designing and implementing the user interface.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. With Tableau, you can keep on asking questions in the data until you discover the root cause. Share your analysis securely. Your entire organization can access these interactive dashboards from any browser or mobile device to find their own answers. Tableau. Answer questions at the speed of thought.
The success of convolutional neural network has been attracting many students and practitioners to learn the exciting technology. However, for beginners, the CNN model is not easy to understand. We introduced the Explainer, an interactive visualization tool to help beginners more easily learn about convolutional neural networks. Using the Explainer, users can progressively explore the single model with real-life images in their browser, getting a comprehensive understanding of both high-level model structure and low-level underlying mathematical operations.
Several recent studies advocated the use of non-parametric density models for the improved characterization of data uncertainty. The non-parametric models, however, present the challenges such as increased memory and computational requirements. In this work, we propose an efficient non-parametric framework for volume rendering in the context of uncertain data and show their effectiveness in classifications via comparisons with the other statistical models.
In our current work, we visually compare two cohorts of segmented and classified tissue images, originated from single-cell omics data. To that end, we developed a data-driven and interactive workflow implemented in a multi-linked view system. Finally, we show the effectiveness of our workflow through specific case studies.
With the proliferation of AutoML systems, it's now easier than ever for non-experts to create and deploy end-to-end machine learning pipelines. These systems explore the model search space and optimize hyperparameters in order to solve a particular task. We propose Pipeline Profiler, a tool that enables the exploration and comparison of machine learning pipelines produced by multiple AutoML systems. By analyzing these pipelines, we have the opportunity to better understand how AutoML systems work and obtain insights that can be used to improve them.
We present StratGraphics, an approach for designing data-agnostic and fully reusable visualization templates. StratGraphics follows the inverse workflow that common data-driven systems. Rather than starting from data, designers construct visualization structures without relying on a data schema. Data tables are shaped later from the structure of graphics. We demonstrate the power of the approach through a gallery of visualization examples.
We present VisInPractice, a tool for
All right, good day and welcome everyone to VisInPractice 2020. We have an exciting program today with topics ranging from design systems to freelancing to molecular animation. On behalf of my fellow co-organizers, we wanted to remind you that while we aren't in Salt Lake City, Utah this year, Our speakers in both the first and final sessions are all from the Salt Lake area to highlight work by our local practitioners. As a reminder, please use the session's Discord channel or the YouTube comments to pose questions for our speakers anytime during or after the talk. And be sure to check out our website for program details and any Discord or YouTube links to kind of take hold of those. We'll be taking questions over either the Discord or the YouTube chat, so feel free to pose them there. And then lastly, we have a Twitter handle at VisInPractice, so feel free to also join us there. I'll post these details over in Discord in case anyone is following along there. Starting us off is our first speaker, and we'll be starting with Alan Wilson today. Alan started his career as a traditional graphic designer with a focus on brand and package. Over time, he transitioned in UI and UX design. In 2011, he joined Adobe and got serious about data visualization design. Today, he creates components, patterns, and guidelines for a wide range of Adobe products with a focus on Experience Cloud. Take it away, Alan.
Hello, my name is Alan Wilson. I am a principal designer at Adobe, where I focus a lot on design systems and data visualization. I've worked on Data Illustrator, Project Lincoln, and Adobe's design system Spectrum, among other things. And I am super excited to talk today about design systems and how data visualization can be integrated into them. But before we get too far, let's
Hi, Sean.
just
Can you hear
dive
me?
in a little bit on what a design system is. So I like to think of a design system on a scale of simple to complex. Brad Frost, a designer who pioneered the idea of atomic design, characterizes it this way, with atoms on the far left, and as you work your way to the right, through molecules and organisms, and eventually up to pages and templates, complete packages, if you will. At Adobe, we have the same idea, but we replace some of those terms with more tangible equivalents. For instance, for styles, we call colors and fonts and sizes styles, and those can be assembled into components like buttons and text fields, which in turn are assembled into patterns, and so on until you end up all the way on the right with full-fledged applications like Photoshop or Adobe Analytics. And a design system lives on the left side of this spectrum. As you go further to the right, a design system struggles a bit, but it's really good at providing guidance and knowledge on the far left. Now, another way we can look at this is through the history of design systems. Before they existed, we had brand guides and style guides like this one from Coca-Cola. The guide explains how to use the logo, when to use it, what colors and fonts it should be paired with, and any spacing and ink guidelines there might be. It's a really important document, and it helps people to create a holistic brand. So if we think about style guides and brand guides, which overlap quite a bit, we arrive at something a little more than that. So this is a style guide I created for Adobe early in my career, but instead of being around how to leverage Adobe's brand, it was around what the different styles should be for UI components like this button. And it was really useful for a time. And it met the needs of designers, specifically UX and UI designers, right? It created a visual design language that we could use. And so we added that to this little diagram. Now, it wasn't long after I created that PDF that an engineer approached me and said, "Hey, Alan, shouldn't this all be in code? Like, it'd be nice to have a repo instead of having to rebuild all these components for every single product." and thus was born a code library. This is several years old, but it provided the components that a front-end engineer would need if they wanted to interact with a style guide and a brand guide. And you can continue to layer on things like content strategy, which provides guidelines around voice and tone and specific capitalization and all the stuff you need there. And you have to have some system for documenting this, as well as standards and processes to keep everything organized and straight. And all together, this is what I would call a design system, right? All these moving pieces. So now that we know what a design system is, let's talk a little bit about what a design system does. Simply put, a design system answers questions. So let's step out of the abstract and into a tangible example. Let's look at Spectrum, which is Adobe's design system. In Spectrum, you have all the guidelines that you would need, whether you're a designer or an engineer or a researcher looking to implement a quick prototype. We have structure here around our design tokens. You can go down to the components and see specific ones like the action button, or we can look at the regular button. And here you'll find, an anatomy of the button, the many different variants it might have, as well as how it should behave in specific situations. We have usage guidelines, the do's and don'ts of how to use buttons correctly. And we have this for all of our components. Now, at the main resource that a designer is going to use as they interact with this is a UI kit. This is a design file, in our case, from Adobe XD, and it allows the designer to copy and paste and leverage components for any mocks they might want to create. So if we open one of those up, let's open up the button one, we see it looks like this. There's a lot going on here. If we zoom in a little, we see that there's two columns, one for each of the main usage, one for desktop and one for web. And you have all the states every button would need to account for, right? It's default, it's hover, it's touch, keyboard focus, and so on. This is a really handy tool, but it's not super useful for an engineer. Engineers are more likely to go to Spectrum CSS. And in Spectrum CSS, they will find everything they need for that same button component, but in the language that they use. And they can download the package, they can sample it here and try out its different variations. We have really robust functionality around accessibility, language support, including left to right languages, or sorry, right to left languages. But if they want something a little more prescriptive than just vanilla CSS, they can go to React Spectrum to get the same thing in React components. And we have other tools as well. I won't go into them right here, but these are all available public open source at spectrum.adobe.com. So if a design system answers questions, it is a logical conclusion that it should answer questions about data visualization. The audience of a design system is very likely to have questions when it comes to choosing charts and styling charts and all the things that a design system is good at. And you may think that the answers to these questions have been pretty well established, right? We have mountains of books. I mean, I've got a pretty sizable collection myself. And you're not wrong, but the likelihood of the consumers of a design system digging through this material is pretty low. Keep in mind they're usually pretty entry level and they aren't super fluent in these things. I want to call attention to one of these though, because I think it provides a good structure that we tend to model in design systems, and that's the Wall Street Journal's Guide to Information Graphics by Donna Wong. You can see here it has simple do's and don'ts, very practical things about what fonts to use and how to use shading and colors and so on to make your charts more effective. Now, the Data Visualization Society, whom Molly introduced us to last year, has a number of resources, one of which is a collection of style guides and design systems that have data visualization as a part of them. So if we look at that, we have this nice big spreadsheet. It's just it's a Google Sheet right now. When Adobe set out to create its data visualization guidelines for Spectrum's, our design system, we spent a lot of time looking at what other organizations were doing, what things they were tackling in their design systems, and what things they weren't. And we came up with this simple rubric around styles, principles, chart choosers, foundation, and rules. And take it with a grain of salt. Some of this was created retroactively, but I want to walk through some of these things because I think these trends can inform the ways that we can improve data visualizations and design systems. And the first thing we see is styles, right? Styles answer aesthetic questions, and they help people strike a balance between form and function. A great example of this is QuickBooks. They not only have categorical color guidelines, but each color is mapped to a specific semantic. Purple is for mileage, and orange is for overdue or warning or critical items. This is really useful, and I think it bridges that gap between form and function. Here we see some less prescriptive guidelines, but still useful from MailChimp around their colors. And we see this specification from the Sunlight Foundation that Amy Cecil put together. This answers a ton of questions that you might have when designing a chart like this. And it makes it easier to create something that's within the bounds of the brand guidelines and within the overall message for the organization. Cato Public Institute has something pretty similar, which brings us to principles. So principles may seem a little squishy. They're kind of mission statement-y, but they answer the question of why. And I think they are most valuable in larger organizations where you need to align a lot of people around some simple concepts. Here's an example of some principles from the BBC. They talk about their infographics being informative, engaging, and accessible. These are their goals, their criteria. And while they're not terribly quantifiable, they are useful in evaluating work in progress and deciding if it, passes muster for publication. We see these most common in larger enterprises, as you can imagine, these for-profit organizations like IBM. Their guidelines or their principles are around understandability, being essential, impactful, consistent, and contextual. Material has theirs. We at Adobe have ours. And again, they're really useful for aligning a large group of people. Chart choosers are amazing. I love chart choosers. They really help people to answer the basic questions around what chart should I use. This is one of the first questions that I asked as I approached data visualization as a young designer 10 years ago. And one of the tools that I stumbled upon was this from Andrew Abella, this simple chart chooser that breaks down all charts around these 4 main vectors: comparison, relationship, distribution, composition, and then further breaks things down. I loved this. I spent so much time looking at this, and it really helped further my understanding of data visualization. There are others. The graphic continuum is an evolution of that first one, and I think it provides a ton of value. Dataviz catalog is one online that I reference frequently. There's also data2viz.com, which is another great take on this. And when we see these applied in the context of a design system, they tend to be a little more bare bones. Here's one from the UK government that's just text, but it answers the same questions around which chart you should use, and it breaks the answers down into those same main categories. You see Google doing this in material design as well. Foundations give us a vocabulary and a background so that we can understand the other guidelines in a design system. Now, we didn't see a lot of these. In fact, we saw very few of them, but I think there's something that we're going to see more of because they're so useful. Design systems have pretty broad audiences, as we've already discussed, and this audience tends to have gaps, critical gaps, when it comes to understanding data and statistics and other foundational elements. When we created our guidelines, we created a glossary of terms that went through some of these elements to fill those gaps. And as we vetted these with different stakeholders to see if they were performing the job that we wanted them to, we found that they fell a bit short. One example is a stakeholder who could not understand the difference between a ratio and an interval scale, an understandably difficult concept. And so we supplemented the glossary with these diagrams and tables of examples to make it easier to internalize this information. And it worked. It's been very effective in people orienting around this stuff. The last thing that we see are rules. Now, these have an obvious and natural fit within a style guide. They're the do's and don'ts of how to build Dataviz. This example from the International Business Standards Association is a great one. As you can imagine, they have a ton of rules and some really good ones too. Here we see ours in Adobe Spectrum. We structure ours with simple do's and don'ts, often with images and simple text. We use this not just for data visualization, but for our entire design system and all our componentry. And here we see some nice guidelines from the Cato Institute. Again, very simple, straightforward, basic stuff, but this is the type of information, the type of questions that we need to answer because this is what our audience needs to be effective. So let's look at examples of some of these questions across design systems. Let's start with a pie chart. How many colors or segments can a pie chart have before it starts to become ineffective? If we look at the Tafford Data Lab's answer to this question, we'll see that they sidestepped it a bit. In their part to whole section of their style guide, they don't even acknowledge the existence of a pie chart and instead point you toward waffle charts and tree maps and stacked bars. Useful, to be sure, but I do find that interesting. If we look at MailChimp, they do acknowledge the existence of a pie chart, but immediately declare it unfit, not recommended, and not effective. Material has a bit more of a nuanced take on this. They point out that pies are not useful when comparing multiple things and to instead use bars, which is good. But if we get to our actual question at hand, how many segments, we finally do find some answers in Lightning, and Salesforce Lightning's design system. And they say between 2 and 5 values. Makes sense. In QuickBooks, we see similar sentiment. And as we go down the litany of these different guidelines, we see that this question gets answered in a lot of design systems, almost all of them. And if we break it down, we see that they all agree that 2 to 3 colors is great. You can have that many segments in a pie chart, and it's going to be an effective pie chart. Now, if you move to 4, we see some departures, right? 3 of the design systems say that's too many. Now 2 more say that 5 is too many, and all but 1 say that 6 is too many. Let's move on to another question. Let's look at axes. Should they start at 0? This is a little more controversial and should be a lot of fun to see what people think. So let's start with IBM and their carbon design system. On the left, you see that they say bar charts should always start at 0. But if you look at their guidelines for other charts, like line and area, they say it's okay to not start at 0. In fact, sometimes that's a good thing. In Salesforce, we see that they just say you always start your X and Y axis at 0, regardless of chart type or data. Bar charts from the VVC always start at 0, and if we go to the Urban Institute, we see that they also recommend that y-axes should start at 0, and with just a few exceptions. So rather than go through all the rest, let's just break this down. Here we see that the guidelines for bars tend to be a little more strict than the ones for lines. This seems to fall in line with the research. I mean, I know there's still a lot of understanding to be gained in this space, but this seems to align with best practices overall. But I think what's more telling is just how many systems had no guidelines whatsoever. I think this is a bit of a miss. This is a pretty critical question and deserves an answer. And if you are a consumer of one of these many design systems that did not answer the question, you're going to be left without any guidance. So what kind of questions should we be answering in design systems? I think is a good question. And if we look at scatter plots and the questions that we came up with when developing the spectrum design system, there were a lot of questions. And some of these have pretty well thought out answers with good research to back them, but most of them do not. Most of them we created answers for out of whole cloth based on random Twitter conversations or personal experience, or just talking to other designers. Now, I'm not saying that's necessarily wrong, but it is interesting how difficult it was to find answers to these questions that were backed up by science. So I think there's an opportunity here. I think these initial guidelines can be viewed as hypotheses, and we can use them as a starting point for further research and understanding. If we look at design systems for data visualization as a whole, we see very few examples that are all-encompassing, that tackle all of these circles. Instead, we see many examples that only tackle specific parts. They have a style guide, or they have a set of UI components in R, or they have a visual design language and some basic principles and do's and don'ts, but they don't have the rest of it. To me, this simply speaks to the newness of Dataviz as part of design systems. It's a natural fit, but it's going to take time for us to mature overall and to figure out the best ways to do this. And so I think there's tremendous opportunity in that. And I think part of the opportunity comes from this pipeline. Again, if design systems are seeking to answer questions, where do the answers come from? Well, I think design systems live on the far right of this pipeline, and research lives on the far left. The answers are coming from the left and flowing to the right. And if we're going to be effective in this space, we need to acknowledge some problems with this pipeline. One of the first is the time aspect, right? It takes time for things to travel down this, and sometimes that time can be a bit of a challenge. I still see design guidelines that are quoting extensively from many of Tufte's concepts that have been largely debunked. The other problem we see is this game of telephone, that a nuanced, detailed finding in research and in publication becomes a really blunt, simple guideline in a design system that lacks that nuance. And I think that can be a bad thing at times. So I want to leave with one question today, and that is this. How can we improve the pipeline of information that informs best practices? Now, I know this isn't a new question. This has been asked before, but I pose it again because I think there's some momentum in this space, and I want to keep up that momentum. I want to see more things like DistillPub and the multiple views in those series of articles in Medium. I want to see more dedicated websites like the University of Washington has for their papers and their applications and their work in visualizations. And I want to see more involvement in things like the Data Visualization Society. I think these are excellent ways for practitioners and for researchers and academics to come together and to discuss these things and align on best practices. I'm out of time, but I do want to take a few minutes to thank the many people who assisted me on my journey of self-training around Dataviz and in the creation of this little presentation. And thank you for listening and hearing me out. If you want to reach out to me, you can find me on Twitter at Alan G. Wilson or the Data Visualization Society Slack, or just about anywhere else at Alan G. Wilson. Thank you. Okay. All right, thanks.
All right, thanks so much for that great talk, Alan. And I think we're ready for that first question from Alex Bigelow. Did you want to get us started on that, Alan?
Absolutely. So Alex asked, what does the process look like to change a set of design guidelines? And this is a great question. Design systems, one of the problems that they address is just that, how to change things over time. And they do that through a system of variables and tokens, so that when you make a change at the token level, it trickles down into all the places that gets implemented. Much easier than tracing down all the different implementations and fixing them at that level. Now, changes to like rules, like do's and don'ts, those tend to live in people's hearts and minds. And so those can be a little more difficult to change, especially once people have taken a set of guidelines to heart. But it's still a great place to do it in your documentation. It might take a little longer for that to trickle down into your organizational DNA, but it all starts with that guidance there. I'll take
Excellent.
one
Thanks.
more quick question, or should we wrap up now?
I have some questions here that I've pulled. So
Absolutely.
One person asked here, like they're curious about your team's decision to provide foundations. This seems like a really useful resource to bootstrap data literacy for your users. However, other design systems do not provide this info in Viz style guides, but also in UI prototyping. Can you speak more about this decision and what role you think design systems play in supporting data literacy?
Yeah, absolutely. So first of all, it is all about data literacy. And that was one of the biggest hurdles we had to getting our particular audience to adopt our design system guidelines, was they weren't comfortable with charts, period. And so that foundation really provides that. And I took a key from all the books I read on it. Like every book you read on data visualization has several chapters on, the psychology behind it and the basic structure of charts and so on and so forth. And so I really just modeled our foundations off that. And I think data viz guidance and design systems is still pretty new, like I mentioned. So we're going to see more of that in the future. We just haven't seen a whole lot of it yet. And even here at Adobe, our foundation section is pretty bare bones. We have plans to ramp up.
Excellent, thank you. Another great question we had here. Are you aware, Alan, of any existing visualization design systems that encompass dynamic aspects? Think of things like animation, interaction, or transitions.
That's a good question. So that tends to be captured at the implementation level. At the guideline level, you can say things, you can in concept and words, and maybe you've got an animated GIF to drive your point home about what should and shouldn't be animated. But really, the rubber hits the road at the implementation for that. So I have seen some stuff in Vega where people have implemented like loading animations and like when the data comes in, it like populates in a cascading way, things like that. I haven't seen anything really like useful per se. It's just nice and pretty and improves the experience, I think, of chart loading. But I hope to see more of that in the future because I think that's something that we can certainly capitalize more than we do today.
Excellent. And I think we have time for about one more question that I'll ask here. And I'd encourage everyone to kind of engage in Discord if you have further questions, or Alan, if you want to engage with people there, I think that would be awesome. So sometimes creators of design systems have to make choices on debatable topics. For example, using a pie chart or starting the axis at zero, as you show in some of your slides. And like, would it be better to specify like some of these strongly as like a hard rule in that guide that work like 90% of the time, or mention that it kind of depends and when those situations depend on like which create more ambiguity there?
Yeah, I feel like this is at the heart of almost every design system meeting I'm in. Is there's always caveats, right? There's always there's the 90% and then there's the 10% caveats. And the question we ask ourselves all the time is, are the caveats worthwhile? Do we dive into all that at the risk of watering down our main message that we want people to take away? Do we complicate our documentation with all these additional things, or do we just keep it simple? And sometimes we land on one side or the other, or somewhere in the middle. But I mean, there's no easy answer there. There's always going to be some ambiguity, and you've got to figure out what's best for your organization, keeping in mind your audience, not just your end audience, but your authoring audience, because design systems advise the Dataviz authors, not so much the readers. And so you have to consider both the readers and the authors in mind when you're writing the guidelines.
Excellent. Thanks again, Alan. That was a great talk. And so now we'll segue into our next speaker. So next we have here Julia Silge. She is a data scientist and a software engineer at RStudio PBC, where she works on open source modeling tools. She's both an international keynote speaker and a real-world practitioner, focusing on data analysis and machine learning practice. She's the author of Text Mining with R, with her co-author David Robinson, and Supervised Machine Learning for Text Analysis in R, with her co-author Emil Wittfeldt. She loves text analysis, making beautiful charts, and communicating about technical topics with diverse audiences. So let's give it up for Julia.
My name is Julia Silge, and I'm a data scientist and software engineer at RStudio. And I am so pleased to be speaking today about data visualization for machine learning practitioners. Data visualization is an important part of the machine learning process in a lot of different ways. We often talk about data visualization as one of these key communication tools that we have when we're facing outward and talking outward about results or about the process. But what I'm going to be talking about today is using plots and charts and the tools of data visualization as a way to make better modeling choices, and how data visualization is a tool of the system designers and operators themselves. When it comes to data sets, these visual ways of perceiving information form how we think about the work that we're doing, how we understand the problems that we're solving and the models that we're building, and how we decide. And I especially want to focus on data visualization as a support or aid for decision making, because building models or machine learning systems is this complicated, involved task. And the purpose of the plots and graphs that we build are so that we as machine learning practitioners are more effective. When it comes to models and machine learning, more effective can have a couple of different meanings, from more accurate to more practically appropriate to even more fair. And we will walk through a couple of those different meanings. I work on an open source framework in R for modeling and machine learning called tidy models. And a lot of the examples I'll be showing today are from models trained with tidy models and use tidy models code. Some of the specific goals of the tidy models project are to provide a consistent, flexible framework for real world modeling practitioners, from people who are just starting out with modeling to people who are experienced modelers. We have goals around harmonizing the heterogeneous interfaces that exist for building models in R, and to encourage good statistical practice. I'm really glad to get to show some of what I work on and build, but a lot of what I'm going to talk about today isn't specific to tidy models and isn't specific to R. And I want to start by asking this question. When do practitioners build data visualization? Asking this kind of question requires us to think about the process of model building itself, and to, if you will, build a mental model of model building. So I'd like to put this out there as a schematic of what might happen during a typical process a modeling practitioner might use, from getting to the point of first encountering a new data set to having a working model. So the model process starts with exploratory data analysis, which is this systematic, iterative process of exploring data to investigate it. Next comes feature engineering. This is this task of transforming our original variables that we have to more useful features for our model. After we have those features, we can start fitting and tuning models. I've represented this here with lots of different small lines, because the best practices here are to use empirical validation systems, to use resampling, where we fit and tune on these resampled data sets, so that we can have a better understanding of how our models are doing. And typically, machine learning practitioners don't just train one model, but instead have several ideas of things they want to try, different sort of flavors of models that they want to go through, and we train many or try out multiple models. Once these are trained, it's time for model evaluation. This is the stage where we measure how well a model performs using some metric that is appropriate for that specific kind of model and problem. Notice that we're not done at this point, because this process is iterative. We come back, we say, oh, what did I learn from this, this first time I did this? I'm going to go back. I'm going to do some more exploratory data analysis. I need to invest some more time in feature engineering. I'm going to go back to the two models that did best and retrain them again with these new things that I've learned and these new features. Also notice that this process ends with some goal or output, like communicating the results to someone or deploying the model to some kind of production system. That's represented in this schematic with a somewhat skinny bar, but really picture that as transitioning to a whole other set of tasks. In this talk, we're going to keep our scope of what we're going to talk about on this, on the everything before then, on this iterative process of building the model itself. So, machine learning practitioners can, of course, make plots at any time during this process, but I want to make the argument that there are two phases of the modeling process where practitioners use data visualization the most. And the first of those is EDA. So I said before that EDA is this iterative phase of investigation, question generation and refinement, and exploring. So this is a phase that some people might think of as like before machine learning and modeling or outside of it. But we're going to see through this talk that the investigations and understanding that we gain during exploratory data analysis have a huge impact on the choices made in models. The second stage, where data visualization is used a lot, is model evaluation. This is the part of the modeling process where a practitioner has trained multiple models and it's then is like assessing, measuring, comparing how well they've performed. So if you were able to come in and like look over the shoulder of someone building a model, these 2 points are the points when you would see someone making the most plots. And the reason why is that these 2 phases of the model building process are the points of most important human decisions. That these are decisions where validation of them can be difficult because they sometimes involve more art than science, and they're full of trade-offs. Practitioners have to make choices between different priorities and are faced with these trade-offs. So visualization is used as an aid or support to carry out these tasks more effectively and make these better choices. So let's dig in a little deeper and talk a little bit more about that first stage, exploratory data analysis. And let's ask this question: why are these plots built? So at a very high level, these plots are built to understand the data. When a practitioner starts out on a modeling project, this is one of these very first substantive tasks being faced. And the reason we need to have this understanding of the data is because there's about to be a whole bunch of decisions to be made. These data visualizations made during EDA let practitioners ask and then refine specific questions related to modeling goals, like what kind of model is appropriate. And this then feeds into the feature engineering phase that we talked about before, and what kind of pre-processing is needed. And all these kinds of questions are ones that modelers ask and refine and answer by making plots during the EDA process. Let's look at just a couple of example ones to get an idea of what we're talking about. So some of these plots take the form of very familiar statistical graphics, like this scatter plot. This plot uses a data set called the Palmer penguins. It's penguins that are observed in Antarctica near Palmer Station, and it maps each observation to a point on the plot with aesthetics of the plot like X and Y, size and color, representing things that have been measured about these penguins. So exploratory graphics like this are important for machine learning practitioners because for starters, they help us as practitioners understand the type and amount of data we have available. And then going further, they highlight the relationships in the data that we can use in feature engineering or models. So if we wanted to, for example, build a classification model to predict the species or maybe the sex of the penguins based on the other measurements that we have of them, the relationships that we discover or highlight or uncover here in this kind of graph inform the steps that we can take moving forward. Plots for EDA don't always look like super classic statistical graphics. In some ways, this plot here is just a scatter plot, but the X and Y coordinates are mapped to spatial information. This plot shows a data set of trees in San Francisco, and we have empty areas here where parks are. That big one is Golden Gate Park, and the color is mapped to who's in charge of maintaining the tree. Is it the Department of Public Works, or is it someone else? If our goal is to train a model to predict who maintains the tree, a plot like this holds so much information for the person creating the model in terms of what kind of model might we want to try, what predictors do we expect to be important, and like what can we learn about the data set just from using it as a visualization as a tool here in our process. So during exploratory data analysis, machine learning practitioners use plotting in many different ways. Modelers make many different kind of plots. So it's important that the tools that we use for visualization during this phase facilitate fluent iteration through lots and lots of kinds of graphs. I have decades of experience of using various kinds of scientific plotting tools, and in my experience, learning about internalizing the idea of the grammar of graphics it puts us a huge step forward in terms of this efficient iteration, and adopting a system that applies this grammar makes this task of asking, refining, and answering questions to get ready to train models go much more smoothly. The plots that I made here are made with ggplot2, which is one of the best known systems that implements this grammar of graphics, and it is a good fit for this kind of task because it allows this kind of flexibility and fluent iteration. So what kind of models are appropriate? The next thing that we try to learn is about feature engineering. In tidy models, we capture this kind of data pre-processing and feature engineering in the concept of a pre-processing recipe that has steps. So you say what variables you're going to use, then you define the steps, and then you prepare them using some training data, and then you can apply that to any data set, like testing data or new data when it comes time to predict. Let's look at another example here. So this is a data set of houses in Ames, Iowa. We have a lot of information about the house characteristics, like how big they are, where they're located, and their last selling price. So this plot shows the sale price on the y-axis and latitude on the x-axis. So there's kind of a big hole there, and that's where Iowa State University is. And then there's some unique and complex structure and price as you move across the city. So we can, we have a lot of options in terms of how could we model that structure. But one option we have is to use splines to build new features for modeling. The thing is, though, that we have to decide how many spline terms to use. So this is 2 splines, and that doesn't look like it captures the real structure very well to me. 5 looks better. I would believe 10. 10 looks good to me. 20 seems okay, but I'm starting to feel a little skeptical. At 50, I no longer believe this. And at 100, this is just silly. So what's great about data visualization during the process of EDA is that we as machine learning practitioners can see and absorb this and use it to make decisions. If you use tidy models, these decisions may end up being captured in code and looking something like this, like with a feature engineering recipe with steps that transform and prepare our data to get it ready for modeling, whether that's dealing with factor levels or creating indicator variables or setting those 10 spline terms as the last line there does. So whether it's for engineering new features or choosing an appropriate model or understanding data quality, data visualization during EDA has a huge impact on what model practitioners do later on. In a lot of ways, it's a foundation on which the rest of the model process is built. It is often possible to estimate the best answer or value or option for some of these choices that we've talked about using empirical methods like tuning the number of spline terms. But it is nearly impossible to remove entirely the element of human judgment from these choices. Or at least it's a bad idea. Machine learning algorithms are astounding. They're incredibly capable of learning patterns from large amounts of data. Vigorous adoption of EDA as part of the machine learning process is one safeguard that we can use against ending up in a situation where you have to ask yourself whether it was a good idea to just deep fry your data. Let's now move on to that second stage, to model evaluation. This is the phase where we have trained and possibly tuned models, so we have predictions, and we can compare true values to predictions and assess how models are performing. If we ask the question here, why are these plots built? At a high level, the answer is to understand the models. And more specifically, we typically start out assessing model performance. This is the point at which we, as model practitioners, have to reckon with questions about success and failure and ask, like, did this model work? Which model performed best? Because typically we are comparing more than one model. We're also interested in how models perform for different kinds of observations, because the process of model evaluation allows us to interrogate subgroups. This is typically where discussions of model fairness come in. A lot of the current work on machine learning bias and fairness focuses on how models perform differently for different groups, and perhaps for different legally protected classes that may not have been included directly as variables in the model, but it is possible that we still see differences in model performance in the final output. Model evaluation is also concerned with understanding why a model is making the predictions it does. So for all of these kinds of questions, practitioners heavily use data visualization for a lot of the same reasons that's used during exploratory data analysis, which are a lot of the same reasons that anybody ever uses data visualization at all. The plots are used to ask and answer questions and show relationships clearly that would be difficult to see otherwise. And they are these supports and aids for decisions that need to be made. In these cases, which model should we use? Or is this model fair enough? At the same time, there are some pretty unique things about plots used for model evaluation that I think are pretty interesting. One is that plots, many of these plots used for model evaluation involve graphical norms or idioms. This plot shows how two model evaluation metrics for a regularized model, a lasso regression model, change with the regularization penalty, like how regularized it is. So someone who is familiar with these kinds of models can look at this plot and quickly recognize whether or not it worked. Whether it's a model that needed a lot of regularization or a little bit, and maybe like looking at that R squared, how well the model fit the data, or in this case, perhaps how not well it fit the data. So this kind of plot is like a shorthand or an idiom that packs a lot of information in it for an expert or a very familiar audience. This plot is similar. This is a receiver operator characteristic curve. It's 10 of them actually, an ROC curve for a model trained on that Palmer penguin data that we discussed near the beginning. And this is a visualization of how well a binary classification model is doing. So the more up in the left-hand corner the curves are, the better the model is doing. The axes have the true positive rate and the false positive rate on them. And ideally, we want both of those to be great. We want the model to be able to do a good job for both of those cases. So this is another example of a model evaluation visual idiom that is very familiar to model practitioners that can be used to compare models, to assess a model, and so forth. So these kinds of visual idioms are a great fit for automatic plotting methods. So when we talked about EDA, I highlighted the need for a flexible plotting framework that can be used to create any kind of plot fluently, and how adopting the grammar of graphics lets us be able to create anything we want in a flexible way. A lot of model evaluation plots are the same every single time we make them. And practitioners can be better served using shortcuts built by tool builders like me and my team, because it can be a hassle to copy and paste the same code for an ROC curve every single time. However, not all plots for model evaluation are these kinds of standard idioms. This is an evaluation plot for a model predicting the class of a volcano, and each hexagon there shows the percent of volcanoes that have been classified correctly within that area on the Earth. So while knowing about some key automatic plotting methods are a useful part of like the toolkit, the plotting toolkit for a machine learning practitioner, having that fluency in a flexible visualization system is very important. There's not always going to be an automatic plotting method or one of these idioms available to visualize model performance in the way that that you need to. Through this whole exploration of data visualization and the machine learning process, we've focused on plots made by system designers and operators for themselves as a tool to make better modeling choices. Often discussions about data visualization center it as a communication tool, and it 100% is. But in this case, we've focused some of data visualization's other functions, like its ability to be used by a system designer to understand the system more fully. I've been interested to see discussions in the machine learning community recently about participatory approaches to machine learning, where the system designers partner with people affected by a system, like the users of the system, to design and implement the system. I think this is going to be interesting to watch because it's going to have to impact choices through the whole modeling process, including what kind of plots we make, what kind of graphs we make. And it may change the answer to this question: who are these plots for? What I don't think it's going to change is the main purpose of any given data visualization. Some plots are created to help us understand the data that we start with, the input. So in investing in data visualization to understand data is like laying a strong foundation. And some plots are created to help us understand the models that we create, the output. So careful visualization practices in model evaluation sets us up for success in models that are as accurate, appropriate, and reliable as possible.
All right. Thanks, Julia, for that really insightful talk. Our first question here comes from Chuck. So about Dataviz at the model evaluation phase, to what extent are these Dataviz pieces used for communication to stakeholders who might be a step or two removed from training in the model? Are these Dataviz pieces mostly meant for the ML practitioner who has been in the weeds with the data all along?
Yeah, that's that's a great question. So many talks and like when we talk about data visualization, we really focus on its function as a visualization tool. And I really have been thinking a lot lately about that is, of course, 100% true. And I'm not like saying that is not true, but I really have been thinking a lot lately about how it has other functions as well, and how it is used by people to understand systems like as they're going along and building it. So I think the model evaluation plots are really interesting case there because they often do require uh, a little bit more domain knowledge to understand what's going on, at least in that sense where you kind of like look at it and you're like, oh, yep, I know what's going on. And are a really good example of that kind of plot where its main function is often used in that way, like by a system designer to be used in the course of designing a system, a little more so than in communication to say stakeholders. So I certainly would never make some grand statements about it's never used for communication or that they shouldn't be used for communication. But I think it's super interesting to be kind of thoughtful about what are some of these main purposes and choices.
Excellent, thank you. And next question from Matt. Are existing or popular visualization tools better suited for some parts of the machine learning pipeline than others? And where in the pipeline are new tools needed most?
Yeah. I am a pretty strong advocate for tools, be they in whatever language someone is working in, Python, R, Julia, for tools that acknowledge and adopt the need for flexible plotting methods. And I think I said this in the talk, but I have used so many different plotting frameworks over the course of my career, like coming from physics and astronomy for so long, and I have been convinced to the idea of like the grammar of graphics, and that some kind of system that implements this gives people who are not deep experts in the data viz. I would put myself in this bucket, like my deep knowledge is in data analysis and machine learning, right? So the idea of like learning about and learning how to apply the idea of a very flexible grammar of graphics get you so far and be able to iterate through many kinds of plots. So I think that the tools that are most suited for the ML pipeline are ones that empower people to build these like flexible kinds of plots very quickly. I think that where in the pipeline are new tools needed most, I think what's actually needed most is more knowledge and research about what kinds of these model evaluation plots work best and why. I showed two today that generally people like and understand and get pretty broad use. But there are some examples of model evaluation plots, maybe like one that's a little more statsy and a little less machine learning-y is the idea of like a QQ plot. And it's one that like research has shown is kind of useless. And so the thing is that it can show you that your model is fine, that you don't have problems like at either sort of end. But if it shows you that something is wrong, it's basically unactionable. Like people look at it and even highly experienced stats people look at it and say, I don't know what to do next. Like, I don't know what to do. Like, there's nothing to take from it. And I think what's really needed in the intersection of data visualization and machine learning is what model evaluation plots work and why. Right now, I think we're operating from heuristic. We're operating from just experience and like, oh, I showed this to people and they understood, and versus we never could get anywhere from showing this. I think that's a really great question, though.
Excellent. Thank you so much, Julia, for those great insights. We're out of time for questions, but I encourage people to, again, engage in some of the Discord chat, and we can keep on, engaging there. So coming up next, our last speaker for this session. Let me pull it there. So we have Jes Ford. She is a sponsored snowboarder turned astrophysicist turned data scientist. She enjoys applying Python data science tools to a wide variety of problems and teaching skills and best practices to others. Jess currently works as a senior data scientist at Recursion in Salt Lake City, where she also organizes the local Women in Data Science Conference and the Salt Lake PyLadies chapter, and spends her free time exploring the Wasatch Mountains. So let's give it up for Jess.
Welcome to Machine Learning for Medicine, visualizations that accelerate drug discovery. My name is Jes Ford. I'm a senior data scientist at a company called Recursion. Recursion is a digital biology company in Salt Lake City, and we have the mission of decoding biology to radically improve lives. We are a company collecting tons and tons of relatable imaging data, building machine learning models on top of that to create a relatable space, and using these models to discover new medicines to treat patients. We kind of cover the whole process from data collection to modeling to refining different medicines and getting those into the clinic. So I'm going to kind of walk through a few different phases in this process as they relate to data visualization. A bit about me. I am a data scientist, as I said. My background is actually in physics and not anything to do with biology, unlike a lot of people at my company. I did a PhD in physics and then a postdoc in data science, and then I worked in industry doing kind of marketing and customer service type work before coming to Recursion. So this is really different for me, but I love applying my technical skills to new and different types of problems. I also like being involved in my community. I run the Salt Lake PyLadies group and the local Women in Data Science conference each year. All right, so this is kind of an overview of the things I'm going to go through in my talk. We're going to kind of start at the beginning of the process, a little more simple. How do humans actually view these multi-channel images that we produce? Then we'll move on to how do we want the machines, the machine learning algorithms to view these images? When we're training models, how do we understand performance and how do we debug weird issues with cheater machine learning models, for example? We're using these models to create maps of human biology. So I'll give you some examples of those and kind of the exciting ways that we're building out our capabilities there. Finally, of course, we want to get to the point of creating new medicines for patients. So how do we assess whether a drug is actually rescuing a disease in this high dimensional imaging space? I'll show you how we compress this into like a human kind of more intuitive visual format. And then finally, once we have a candidate medicine, before it can actually be given to patients, we need to, as much as possible, remove any risks associated with, for example, heart disease or liver failure, all kinds of things that can go wrong when you're giving compounds to patients. So we have some great visuals that help us convey those risks and the uncertainty associated with those risks. So to give you a little bit more detail about the data we're collecting, our bread and butter is this imaging assay. So we have labs full of robots that are moving around these plates and dispensing cells and compounds and different types of liquid reagents and taking images. So we run hundreds of imaging experiments every week, and these are done on these plates like this cartoon on the slide is showing. Inside these plates, there are many, many tiny wells, and this is where we actually put human cells and the drugs or whatever reagents that perturb the cells, and then we take images of those. So these images are where we're going to start. So the first visualization I want to show you, we're starting simple here, is just how do we visualize these multi-channel images. So here's an example. We apply dyes to these cells that will highlight different physical regions of the cell. And then we have a channel for each of those different dyes. So for example, these are all the same cells shown here. And on the top left is the nuclear channel highlighting the nucleus of the cell. And then as you can see, there's 6 in total channels in our standard imaging assay. So we can't just map this to RGB, you know, red, green, blue like normal, but we can still map these to 6 different colors in the RGB color space, and that's what we do. It's really pretty simple, but we choose 6 different colors that are easy to kind of visually distinguish, so that we can pick out, you know, the Golgi and the nuclei in these composite images. And we actually have publicly available code linked here at the bottom for doing this. We had to release this code, or we didn't have to, but we did release this code as part of a big public data set that we released last year. So this was exciting for us. This was our first time really putting a large public data set out there, and we've had more since then, and they can all be accessed at rxrx.ai. So this first data set, this is called RxRx1, and this is a data set designed for studying batch effects. So batch effects are a common general problem in biology, where if you apply you do some biological experiment, if you do it different times, you'll get slightly different effects, and not just due to noise, but due to actual different conditions in the lab. Even like temperature, humidity can change the way cells behave. So this slide is showing you some examples of a couple different types of perturbations. These are called siRNA. They do kind of like a gene knockout type of disease modeling. These are 2 different rows for each of those perturbations, and then we're showing it in 4 different batches. And so you can see, like, these are visually very different, and we want a model to be able to distinguish these different perturbations, but to be able to generalize across these different batch effects. Yeah, so this RxRx1 data set had more than around 1,200 different biological perturbations, and these were across many different batches and actually 4 different cell types. So the first cells I've been showing you are HUVEC cells, but there were 3 other cell types in this data set as well. And we, along with the public release of data, we hosted a machine learning competition on the Kaggle website. So this was a huge success for us. There were lots of teams and individuals who competed in this challenge, and the leaderboard is shown here on this slide. So the scores over here on the right, these are accuracy scores for a 1200 classification problem. These are really, really good. And we learned a ton by studying the techniques that these competitors used. So that brings me to my next visualization. One of the things that we learned from these competitors had to do with image augmentations. So image augmentations are a technique in computer vision where you kind of modify your images slightly as you pass them in to the deep learning algorithm as it's training. And the idea here is that you're kind of showing the model many different variations of the same image, and it kind of helps prevent overfitting by always seeing the exact same image. And really common techniques are just to do like flips and rotations of the image, for example. But what we learned from this competition is that really, really strong image augmentation techniques were very successful. So here I'm showing a couple of those techniques that competitors used. So, and these involve actually mixing together input images. So on the left, I have two different images A and image B of cells. And one approach to augmentation is called cut mix. And you just basically take a crop of one of those images and you insert it into the other image. The other technique that people use is called mix-up, and this is an actual like averaging of the pixels in both images. So you're just kind of blending the two images together. And these are really strong augmentations, but they have been shown to be effective in other machine learning competitions, and we were excited and surprised to see that they were really effective on our cell images as well. All right, so we've got some machine learning models, and we want to understand how are they doing? How are they performing? This is not, you know, any groundbreaking visualizations here, but we use TensorBoard to view the progress of our models as we're training. And the usual technique, which is what we do here, is to compare the loss and some other metrics such as accuracy, and to compare those for your training data set and your validation data set as you are training your model. And here I'm just showing a couple of different models in orange and blue that we were comparing in the study that I pulled these screenshots from. What you can see here, if you look at the loss for the training data in the orange model, is kind of continuing to decrease slightly. So it's continuing to fit the training data increasingly well. But the validation loss in orange, you can see, is kind of bottoming out at around, you have 50 to 100,000 steps in this model. So we can see that the model is not learning any new generalizable information after a certain point. Okay, so this is how we kind of like assess models while they're training, but then we want to figure out, like how good are the predictions on our validation or our test data. And to do this, we find confusion matrices to be extremely helpful. So you might have seen confusion matrices in the 2 class, like the binary classification problem. So you've got your it's a 2x2 square, and you've got your true positives and your false positives and your true negatives and your false negatives, and it's much more simple. Here we're dealing with typically hundreds of different classes, maybe hundreds of different siRNA or other compounds, things that we're trying to classify, and so this confusion matrix becomes tiny little squares. So here, just like in the binary case, we're plotting the true class versus the predicted class. And so if a perfect model would have a really strong diagonal here. And so this is hard to see because these are tiny dots here, but the diagonal shows you cases where the true class was correctly predicted. But what's really interesting for debugging models is to take a look at some of the patterns that appear here. So there are some vertical striping features in this confusion matrix. And those are examples of classes that the model is always wanting to predict. So regardless of the true class, the model very frequently predicts the one class. And frequently this can happen if you have an overrepresented class in your data set. So machine learning models, they're learning patterns, and they're going to learn whatever the easiest pattern is that lets them make good predictions. So if the easiest thing to do is to always predict the majority class, it's going to do that. So that can happen due to this effect. It can also happen when you have like a really unique class that's easy to identify in your data set, or that is easily confused with other examples in your data set. So this is a useful technique when we're debugging models. So once we get a good model that we're happy with and we put it into production, what we're using that model for is to embed our images, to basically take an image as an input and to spit out a vector of numbers. It might be 100 dimensions, it might be 1,000 dimensions, but it's some featureization that represents the images, and that's what we use for downstream analysis tasks. So what can we do with those vectors? One of the really ambitious things that Recursion is doing is to actually build out a map of human biology, to understand like complex relationships between all different types of things that can like happen to human cells. So we have these vectors representing images or representing perturbations, a vector that represents a specific compound. And we can ask how similar is that vector to another. We can calculate some type of similarity metric, and we can plot these in these correlation heat maps. So on the upper left here, this is a soluble factor correlation heat map. And so it's got the same soluble factors on each of the two axes. And so the diagonal, any perturbation is perfectly similar to itself. So the diagonal is 1, and the red is showing you soluble factors that are very similar to each other. Blue is showing you ones that are very different from each other, and then white is, they're kind of, there's like no real relationship. They're randomly oriented vectors relative to each other. And you can do the same thing for compounds and the same thing for genes. Do we do CRISPR knockout of genes in our cells and featureize the images from those to produce an embedding. So this deep learning space gives us kind of like a universal way to compare perturbations across like all different types of biology. And where this becomes really powerful is filling in these gaps. So we might never have run an experiment that was directly comparing the one compound and one gene, for example, but we can fill in this space of the similarities and differences between soluble factors and compounds, soluble factors and genes, etc. And so this is like an early stage version of Recursion's map, and this is kind of the direction that we're going in and iterating on and improving. And it allows us to kind of like explore and find like, new relationships. Maybe a compound has a opposite effect to some gene knockout, and we think this might lead to some treatments or give us some insight into like really complex biology. All right, so we have these vectors that represent our perturbations, and we want to ask ourselves, we want to create medicines for patients. So we need to know, does a drug rescue a disease? So here's a easy to see example of some cells that have a disease on the left, and then a healthy control of those same cells on the right. So if we take these disease cells and we actually know a good treatment for them, we can apply that treatment in increasing concentration. And if this like really treats the disease, we would expect these healthy cells to look, the disease cells to look increasingly like the healthy cells. And so this is easy to see by eye here. So it's a good example for a slide, but in a lot of cases, it's hard for a human to see these effects, and we rely on the machine learning models to kind of pick out these small differences. Okay, so we can see this by eye, but we need a way to represent this so that we can, do this analysis on many different types of diseases and drugs. So what we do is we use a plot that looks like this, and I'm gonna walk through this because this is definitely like a complicated thing maybe to see for the first time, but basically we represent the space that we care about in the context of a certain disease in terms of these two axes. So we have like the disease score axis, and then we have the off disease score, or sometimes called like a side effect score. So ways in which cells are affected that are unrelated to a disease. And since we do we take many different images of different cells under the same disease. We have like lots of samples. We can create these sigma contours that demonstrate like the healthy cells live in this region of the space. The disease cells lived somewhere over here. And then the disease cells that have been treated with some compound are represented by these dots and lines. And so these show these trajectories through this space as you increase concentration. And so, for example, the lime green line here is showing, some compound C in this example that is moving the cells from a healthy space further and further towards the disease space. This dark green line is showing something that does a similar thing. It moves things towards healthy, but it also has a large side effect. So there's something else going on unrelated to the disease that is noticeable in the cells. So a different way to kind of explain this, I'm going to borrow from our VP of data science, put out this great tutorial using cat GIFs to explain explain these exact same plots. So the analogy in 3 dimensions is that you are a cat on the dresser and you want to jump to the bed. So you think of the dresser as being like the disease cloud, this pink region of space, and the bed you're trying to get to is this healthy space. Okay, so there are, in this example, there are 3 different dimensions that you can move in, but the only dimension you care about is that vector directly from the dresser to the bed. So you think of that vector as defining this change in on disease score. And if you, like this cat, missed the bed, you don't care in which direction you missed, you just care that you missed. And so all other directions, all other types of changes in the cells in this like high dimensional representation are all kind of represented in this off disease score. So here are some results from a very timely screen that we did earlier this year. So we were fortunate enough to partner with some local universities to run some COVID-19 screens. These were cells that had COVID-19, and we treated them with lots of different compounds, including some of the names that you hear in the news, like remdesivir and hydroxychloroquine. There's an additional compound shown here, this Jes 441524. This is just like a very similar sister compound to remdesivir. And so what we were able to show using our deep learning embedding representations of cells was that in human cells, on the right here, in human cells, both remdesivir and its sister compound seem to do a great job of moving the cells from this disease space back to the healthy space. Hydroxychloroquine actually veered off in the other direction and had really large side effects. What's interesting about this result is that we also repeated the same experiment, not just in human cells, but in these Vero cells, which are this African green monkey cell type, which was used in a ton of the early COVID work by other groups. And these other groups had shown that hydroxychloroquine might actually have some efficacy. And it turned out when we ran these experiments, we did actually see hydroxychloroquine in the monkey cells does seem like it moves in the direction of rescuing these cells. There's still a very large side effect, but this leftward shift that we saw with the monkey cells, we didn't observe with human cells. And so this was a kind of first glimpse for us that remdesivir was probably a much more promising compound for treating COVID-19. We have released this, our COVID-19 screening data set. It's also at rxrx.ai. It's called, this data set's called RxRx19, and yeah, it's freely available to check out and download and build models with. So I encourage you to check it out if you're interested. Okay, so that brings me to the last visualization that I'm going to talk about today. This is a visualization for de-risking medicines. So we have some compound, you know, from the last example that we think rescues a disease. We need to make sure that we don't have, aren't giving people liver failure or heart issues, things like that. So we've developed this plot that kind of contains a whole bunch of different information at once, and I'm gonna walk through this. So there are data points on this plot that are generated by a biologist who runs a specific assay for a specific compound, and this is measuring the extent to which there's some liability. So that this could be, for example, a liver failure assay. And we are showing distributions on the sides of this plot that correspond to parameters of the fitted model. So we are fitting a sigmoid curve model, which is just a thing that kind of, in these examples, will start off somewhere around 100, kind of decreases down to 0. This is like a standard type of curve for this work. And so these distributions on the side are showing the posterior distributions for different fitted parameters. So this is the max effects, which should be somewhere around 100. The min effect is somewhere around 0. And then the parameter that we actually really care about is the EC50. So this is the concentration at which the compound has half of its effect. And so we're showing with this vertical line the point where this probability distribution is maximized. at 27 micromolar in this case. And then we also show for comparison predictions from a machine learning model that predicts the liability measures for this compound. So here's a few different examples of these types of plots. And why these are really powerful is that instead of just telling the biologist or the chemist, you know, the EC50 is this one value, we can give them a sense of the range of allowable values given the data that they have. So in some cases, we're only able to set upper bounds or lower bounds on EC50, and we might need to go back to the lab and collect more data. There are cases where we get some kind of weird bimodal structures, and these are just really helpful visuals for the chemist to decide and kind of assess the risk of this molecule. Maybe they need to do some iterations on it and see if they can bring the EC50 concentration into a more acceptable range. All right, so here is what we just talked about. So we walked all the way through from collecting images and viewing them, how we feed them to machine learning models, how we assess those models, how we use machine learning to create a map of human biology, how we assess, you know, the medicines that we're producing. Like, do they rescue diseases? And then are they presenting other potential downstream risks to our patients, such as, you know, heart disease in this example? All right, so that is it for my talk. I want to thank you all for coming. I've got some information here. I'd be happy to connect with any of you in the future. I've also got some links here to our public data sets that I talked about. And Recursion just raised a large Series D round, and we're hiring for all kinds of positions. So if you're looking for a job, I'd encourage you to check us out.
I'll keep
an
eye on questions.
Thank you very much, and enjoy the rest of the conference.
All right, thank you so much, Jess. See some virtual applause there. Feel free to post any questions you have. I have some questions prepared otherwise. So one thing I was curious about, it seems like we had a lot of complex visual plots in the talk today, like combining a lot of information packed into a single visual. And so I'm curious, like, how do you and your team handle like communication of a lot of these complex visual plots? Are they used internally, communicated with external stakeholders?
Yeah, good question. A lot of the plots I showed are used internally. And they definitely, there's a lot there. Like, it takes a while to explain some of these. Like, we try to keep things as simple as possible and get rid of chart junk and like get to the point. But you know, we're dealing with really high dimensional data, and sometimes there's like multiple things that we need to show in one plot. So definitely these are all tools we use internally, but some of them have been started to be using externally as well. So we have a few papers out in this last year on COVID-19 and some other work that use these plots I showed with the disease axis and the off disease score, like the cat GIF plots. So those are things that we're also using externally. And yeah, I think they take some explanation, but yeah, it's a challenge with the kind of data we're trying to show.
For sure. Another question I had are like, what would you say is like the biggest or some of the biggest challenges that you face at Recursion when it comes to using some of the like data visualization in your work?
Definitely the size of the data. So going back to those cluster heat maps that I showed, where you know you've got maybe different genes or different compounds on each axis. The examples I showed there were simplified and cut down to like a number of compounds that you could fit on a plot and zoom into. But frequently we're screening thousands and many tens of thousands of compounds. And so figuring out ways to to simplify and reduce down to a set of interest for the biologist or the chemist that needs to inspect it is tricky. And I think actually going back to one of the questions that was asked of Julia in the in her section was about whether machine learning practitioners use interactive visualizations. That's actually a tool that we use a lot for these. So we build like simple web applications using Dash app to allow biologists to zoom in on those heat maps and to like explore interactively. Because otherwise, I mean, a static plot is like, it's way too much information. So that is one tool that we're using for that.
Excellent. So it sounds like scale is one of the big challenges. And I'm curious, is it more like scale, like how much you can fit on the screen, or more like just there's so much data that it takes a lot to like of power to process it and get it to a point where you could even visualize it, or maybe both?
Yeah, it's both. Definitely. Like fitting it on the screen can be a challenge, but it's also, you know, even if you can figure out a way to fit it on the screen, making sense of it. And you know, I think especially in, and this is probably true in other areas too, but especially in biology, you know, the scientists who we work with have a ton of domain knowledge, and they have a ton of background in, like, for example, what they expect to see in the data. And so like one of the challenges that we face when we give someone, you know, these heat maps maybe have 100,000 different values in there. Like, how do we help people find the useful information and as much as possible prevent like any kind of cherry picking, right? Like if you have some idea of like a relationship you expect to hold, it's easy to like zero in and like have this confirmation bias of like, oh yeah, I see these particular things that I know should exist and therefore this is right, and to kind of gloss over some of the other relationships. So you know, picking out the most significant relationships that exist and being able to just summarize those and present them to our stakeholders internally is one of the things that we struggle with and spend a lot of time on.
Excellent. Thanks so much, Jess, for diving into that and for an excellent talk. Let's give it up for both Jess and all of our other speakers today. And we look forward to seeing you after this short break to dive into some more talks and then a panel discussion. Thanks, everyone.
Program developers spend significant time on optimizing and tuning applications. But working with binary code to understand what compiler optimizations were applied can be challenging. We present our visual analytics system, CCNAP, designed to identify and assess compiler optimizations in binary code. Check out our paper to learn more.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau, answer questions at the speed of thought.
Suppose you want to see the overall structure of a new project repository. Using Git clients tools, GitHub Network, or Git log command is quite burdensome to get overview and navigate data. We presented Githru as an interactive visual analytics system for the Git metadata to help users explore and understand the context of development history.
Deep neural networks are vulnerable to maliciously generated adversarial examples. This brings high risk in applying these networks to safety-critical applications. We developed a visual analytics approach to explain the root cause of such wrong predictions. Our contribution contains a constrained path extraction method, a river-based visualization, and a contribution analysis method.
Tableau helps you see the stories in your data. It's designed to help you be smarter, so you can make better decisions faster. Connect to the data you care about. Sort, highlight, drill down, or filter your data in seconds. Add calculations to extend your data. With Tableau, you can keep on asking questions in the data until you discover the root cause. Tableau. Answer questions at the speed of thought.
We present Lyra 2, a system for designing interactive visualizations by demonstration. To design interactions in Lyra 2, users directly manipulate the visualization canvas. The system interprets demonstrations using heuristics and suggests possible interaction designs. We find that Lyra 2 enables rapid prototyping of an expressive range of interaction designs. We're excited to share this work with you.
Data videos are quite popular nowadays. They usually show changes in the data. However, creating a data video requires multiple skills, and the process is usually laborious and iterative. Our approach focuses on automatic and interactive visual enhancement of important changes in time series data with data video.
Position is believed to be the most precise encoding channel, but our perception and memory of it can still be biased. Past work has shown that the vertical position of bars in a bar chart is recalled in a biased manner, illustrating both an underestimation and overestimation bias of position. Here we find that the aspect ratios of the bar marks can cause this position bias, specifically resulting in overestimation for bars with wide ratios and underestimation for bars with tall ratios.
We present transfers,
a design study that is proposed to analyze and integrate close and distant reading of multiple translations. TransVis presents the overview of the collection to capture global patterns that is facilitated by the ADM-VIV matrix. TransVis integrates a detailed view to explore interesting path of alignments. We also propose the TLC view to examine and explore the terms of the user selected path to justify and reason the AD analysis.
Morse complexes have shown a great utility in understanding the topology of complex scientific datasets. The noise in the scalar field, however, can significantly distort the Morse complex topology. Hence, we study the extraction of Morse complexes for ensembles of noisy scalar fields through their uncertainty visualization using our proposed statistical summary maps.
CarxS is an authoring system which enables rapid creation of zooming-based scatter plot-like visualizations in just tens of lines of JSON. We contribute a declarative grammar for such visualizations, which captures a large design space. By working with multi-node database spatial indexes, CarxS enables interactive browsing of billions of data points. Come listen to our talk to learn more.
We propose a new semi-automatic method that uses topological features to guide users in tracing neurons, and integrate this method within a virtual reality framework. We use the Morse-Mel complex to find a set of candidate neuron arcs. The candidate arcs are integrated into a VR neuron tracing system and exposed through our Morse-Mel complex guided semi-automatic tracing tool. The topological ridge graph underlying our MSC guided tool is robust against gaps in the signal.
Out-of-distribution samples refer to the test samples not well covered by the training data, like these black cats. They are misclassified with high confidence due to their black bodies.